Hey guys, welcome back. I'd just like to start by mentioning that I'm a little sick right now, so if my voice sounds weird or anything, that's probably the reason why. So, this episode's mostly going to be refactoring because, like I mentioned in the last episode, my previous design, it was really new and it didn't have every consideration that I really wanted it to. So I've been redesigning it. And so I've also mentioned that we're going to be storing values at compile time to an extent for like future reference, so that when we're dealing with arrays, we can know if their sizes are valid, that they're not like negative, etc. And it also allows us to determine if we're dividing integers by 0. So I just want to give you a bit of a showcase of sort of where we're headed. You'll notice this is Kotlin/language instead of YouTube lang, because this is the like base thing that I'm writing in my spare time that I'm copying from on the right. And so I just have a small like test file here with just like 2 examples basically. Well, I guess 3 lines. Firstly, there's just a simple subtraction. There's a bitwise operation, which I'm kind of questioning if I'm going to keep the exclamation point for bitwise. What I might do is I might keep the normal logical operations as well as the like not and or word keywords, and then this would just become the bitwise. But for now, this is just how it is for bitwise, because this is the only bitwise operation we've actually implemented yet. I'm pretty sure we've done that on both of these by now. And here's just like something that would be valid in a language like JavaScript, which should never really be valid in most languages, in my opinion. So if we run this, you'll just see sort of what we'll end up with. So first we get some errors, which is good. We can't perform bitwise operations on non-integer types, and it tells us the type, which is real 64, which is the default type here. Now I also have renamed some of these types, so I'll get into that in a bit, but you can also see that you can't operate on string and int32. There's no operations in which you can merge those things. We might in the future allow you to like multiply, so you could do like a Kotlin string multiplication, a Python string multiplication, where if you have like the string 1 times 2, that's going to give you a string containing 2 ones, something like that. But so the way I've decided to show this, here's our normal like AST printed out, but for the verifier, I've added this verified AST, and you'll notice it's the same thing except it says file statement of type unit, and it has some unknown compile time value. And so when you come down to like the additive expression, you see it's of type int32, because these things are of type int32, which I could display, but I'm choosing for now to just not. And you can see it calculates that the compile time value should just be -5 here, because it's 15 minus 20, which is good. Now, I'm only storing the long value because that's what we need for array sizes, but what has occurred to me today is that long term, that's not going to be good enough, because, and I think I can show you guys this. You can see, sorry, I hope this didn't blind you. You can see that in C, the language we're going to transpile to, you can do things like this. You can do a like calculation in like floating point numbers, and then cast it to an int, and then that's still a valid like array size. And I technically would also want something like that. But if I go back, and you can see, even though this is a 5.0, it says that it has an unknown value because it's not like it's not an integer type, so I'm not storing the value. But I can't just store like 5 as the integer value for this thing, because what if you had like 5.5 and then you wanted to add another 5.5 to it? Then my compile time would think it's only 10 when it should be 11. And so I'm not sure how to handle that. What I could do is I could just have complex numbers, which is like the highest level number that we have. I could just store those using 2 doubles, and then I could just calculate values that way. But the issue with that is our language supports long doubles, and the issue with long doubles is that they don't have a fixed size. They're just like bigger than doubles, which means that they have more precision than Kotlin can like inherently support. There are like big decimal classes in Kotlin or something, but you're supposed to like specify how much precision you want, but the issue is it's like arbitrary precision because it's based on the architecture you're compiling to. But all of this stuff is just like because I'm trying to make my language as portable as possible. You really probably don't have to worry about that in most cases. I mean, this is also just so people can do stupid things, right? Like making your array size some floating point thing and then casting it to an int, which is something people are like never really going to do. And if they're not allowed to do it, it's probably not the end of the world, but I just feel like it should be allowed. So I'll have to be thinking about that, but for now we're just going to only allow the long values. But so that's basically where we're headed, is to get something that's sort of like this, and you can see that all these just have their types. Okay, so now we can actually begin, and first thing I'll have you notice, is there is no more basic type, because I knew it was redundant when I was writing it, having to write all of this stuff. So we're going to end up just deleting this file, though I will say you probably will want to delete it at the end, because following along, it might be easier to copy paste some of these things rather than retype them, but I'm going to probably just retype them. So there's another few things I've had to come to terms with. You'll notice some of these keywords here are actually different. Some of them I've just moved the order of, but you'll notice there is no more nat keyword. There is no more int keyword, real, or cplex. And I've also added the max keywords, which I'll have to get into in a moment. But basically it all comes down to how we're going to be implementing this in C, because as I mentioned before, we for our language are not going to be using the fixed point integers in C, simply because they're not defined on every platform. You can use them if you want to guarantee that you're using those for some reason. I mean, it makes sense, right? But we're going to use either the least types or the fast types, which are guaranteed in standard int.h. And so something else we should probably allow is an int max, because that's also defined there. And that's just going to reference the largest integer size that you have. And there's a signed and an unsigned one. And that's just useful because hypothetically your system could have some outrageous size, and this is just the largest one. And so people will have access to that on their systems using your language. And so accordingly, another thing I've mentioned before is nat and int were going to compile to int and unsigned int respectively. They weren't going to be any of the like least size types. But the issue with that is it's up to the compiler to decide how big those things are. So how can I assume that it is going to be like 32 bits when it's not always going to be 32 bits on every system? And so that would affect implicit casting. So what I've done for now is I've just set 8, 16, 32, 64, and max. And then I've also renamed the real and complex types accordingly, which I do prefer because doubles are 64 bits. So this is a bit more reflective of the actual reality. And then I'm just using the max because long double is just the largest sort of real or complex thing that we have for now. And in the future, we'll add other things in here, but we're not going to worry about that right now. But so this is our whole expression type class now, and it's basically just one big thing rather than two separate things, because I don't really see the utility in that. So I am going to delete this, but as I mentioned, you may want to copy paste some of those things, especially if you don't want to rewrite the enum. And now we can go into expression type. I kind of want to just delete everything and start from the beginning, personally. I'll leave this though. So one thing we're going to need is we need to import Kotlin math.max, and we're just going to use that later. So I probably, instead of saying basic type, I'm calling it the base because it's the base of the expression type. And so instead of calling it B type, I'm just calling it the base because it's just, you know, the base of the type. I'm still making these expression types immutable, but I'm like questioning on if I can make them mutable and hypothetically save on memory. And it doesn't really matter though. If we come to that, we'll, you know, do that far in the future probably. So we're going to simply make a very small enum as our like representation of our types. And we're not going to have any sort of like casting priority stored as part of the enum. We don't really need that. So we can have our any type, which represents, it's mostly going to be used for optional none, so that it can be assigned to anything. Unit meaning it just returns control flow but not a value. Boolean char. Another similar thing is char is super annoying. Some of these decisions that they made for C are so annoying when we're trying to transpile into it, because chars, in C, size of char is always 1. That is guaranteed by the standard. But that does not mean that a character takes up a single byte in memory. It's just, this is guaranteed, but you can have your character be 16 bits or 11 bits in, like, that's totally valid. So the issue is, you could even have 32-bit characters, which means, again, before I was just assuming, well, char can just be less than a nat8. You know, it's equivalent to that because it's a byte, but that's not true on every system. So in order to make my language as portable as possible, I'm not going to allow implicit casting from chars to numbers. Meaning, it's up to the programmer to decide to know their system, so that if you have a character and you want to treat it like a number, you have to cast it, and you have to specify your size in the type that you're casting to. Which means, you know, it's just like overall less ideal, because I don't think I'm going to allow an expression like this anymore. I think you'll have to cast either this to char or this to an int, which is unfortunate, but it's kind of, without making this language less portable, that's kind of just how it is. It's like, there's only so many decisions I can make. A lot of them are forced on me by the fact that I'm transpiling into C, which is, I suppose, something to consider when you're picking a language to transpile to. And the cool thing about this series is you really don't have to follow along in the sense that I'm going to be transpiling to C, but you could write like Rust or Zig or Go or like anything else if you really wanted to. The rest of the code is still going to be the same. It's just you can make different language decisions for your language. So then we have our unsigned natural types. In this case, just 8, 16, 32, 64, and our max, and our int types. I'm still somewhat unsure about implicit casting between all of these, but for now we're just going to go along with that. And then we have our real 32, which is a float, our real 64, which is a double, and our real max, which is a long double. And then similarly, our complex types, 65, ooh. Complex max and string, which should be all that we really need right now. So the one other thing I'm adding in this enum is just a simple way to determine the size of these things, because you'll notice our nats have a size, our ints have a size, our real and complex have a size. Everything else doesn't. But it would be nice if we were able to very quickly access what that size is without actually, without like having to do a big map every single time, because we don't want to have to do a big when statement that says if it's a nat8 or an int8, then it's 8. We don't want to have to do that. So let's just do a small one here. We'll give it a, and it can be a property because this is just an enum. It's just a, it essentially, I'm sorry, like I said, I'm sick, so my brain's a little slow. But since this is an enum, there's only like, each of these is essentially kind of like a singleton. There's just one of them. So we can just give it a size property, so. And the easiest way to check this, the laziest way, instead of making a big list, we can just check if this character is in the name. Because we know that the only time that 8 is in the name of one of these is when we want it to be of size 8. So we can just check against the name. And we still don't really want to have to say 8 in name every single time. We don't want to do this every time, which is why we're making the size property. But it's essentially what you expect. Kotlin's nice. Unlike Java, it actually has unsigned types built in, at least as of some version. 32U, 64 is for U. And for our max, what we're going to do, You technically could choose anything, but I'm just choosing uint.maxValue, which will give us the largest possible unsigned integer. And if there is none of those in the name, we can just return null, because that's something like any or unit or bool or char or string, which don't actually have specified sizes. And that should be the end of just the base. Now we can begin work on our actual expression type and build useful properties. Some of these we're not going to use immediately, but some of them we will. So one simple thing is this thing a natural number? And we can make all of these properties because the expression type is immutable. So at this time, it will just be given a base which can never change, so we can just check. If nat is in the base name, this thing is natural. That's pretty obvious. Now, is going to be true if it's a natural or an integer. Because when I'm saying integer, I don't mean int. I mean, like, is this thing an integer in terms of the mathematical, like, concept of the integer set, z, right? And so the naturals are a subset of the integers, which means it's an integer if it's a natural or if int is in the base name. And these will be useful further down. As you can sort of see on the right, these things will be popping up here and there. And then similarly, is this thing a real number? And when I'm saying real here, I'm again saying the set of real numbers. And so integers are real numbers, but also things that are labeled real in our types are real numbers. And then lastly, you could say is complex. I'm just going to say is number. Well, it's a number if it's real or if it's complex. And lastly, can we operate on this thing? Well, if it's not optional and the base is not in this list of base.any and base.unit because we can't operate on those things, then yeah, we can operate on it. Let me quickly write this. And we also would like a way to print out these things. As I've shown you, we actually will end up using that. So we can say that the result is base.name. We'll just start with the base name. And then if it's dynamic, this should be exactly the same as before, but I'm just going to retype it. We can just add the hash before to specify that it's dynamic. If it's optional, then we can just add the question mark after. And then we can just return result. Now, instead of calling everything implicitly cast, I'm preferring to use the word coerce because type coercion is another name for implicit casting. So I'd rather say coerce instead of implicitly cast because that's just so much more typing. So we can have a coerce to. And we want to coerce this type to some other type. And similarly to before, we'll be returning an optional, or in Kotlin's case, nullable expression type. And okay, now we just have to go through a bunch of lines of logic to figure out when can we coerce these things. So if our type is optional, but the type we're trying to coerce to is not, then we cannot do that. You cannot coerce something that is optional to something that is not optional. Meaning, for example, in Kotlin, if I val x of type int equals null, you can't do that because null is optional and int is not optional. So you can't coerce null into being not optional. So that's the obvious case. And then, well, if the bases are the same, then we can just assume that it works. We don't have to worry about it. Now, if I'm not a number, this current type, and the type I'm converting to is not a number, well, then we can't coerce between them, right? If they're two different types that are not numbers, we can't coerce between them. And I'm sort of, there's an interesting idea with this type coercion, like when are we utilizing this? As I've mentioned before, we're going to utilize this when we're doing operations, that's one time. But there's also a few other times. Hypothetically, we might use it when we're passing in our arguments into functions, so you can coerce to match parameters. And during assignments are other times that we're going to be doing this. So one thing I might add in the future is if you're trying to coerce something of type any, it just works. I don't have that in yet because I don't have assignments in yet, so I don't need to worry about it. But in the future, that might be something we'll have to add. And so now we know that both of these types are numbers. So, okay, let's check out the sizes. We can safely assert that the sizes are not null because they're numbers. So as we can see in our definition above of size, since it's not a number, based on the way we have our type set up, every number has a size. So we can just check if our size is smaller than type.base.size. And you'll notice one thing with this smaller thing. If I'm a nat64, I will not be smaller than a real 32. But you don't have to worry about that because we're only going to use smaller when we know that they're the actually like same type, when we're comparing like a real 64 to a real 32. I'm just doing it up here so that we don't so that we just have it stored, and then we can just utilize it below. So okay, we have two numbers. What if the thing we're trying to coerce to is an integer? Well, if what we are is also an integer, and we're a smaller integer, which you'll notice when I say smaller, I mean less than or equal to, so it could be the same. So if we're trying to coerce to an integer, and we're an integer, and we're smaller, then we can coerce to this thing. Otherwise, we can't. And so that means, you'll notice I'm allowing naturals and integers to just be coerced to each other. Meaning, if you're trying to coerce a nat32 to an int32, it's allowed, because they're both integers and they're both the same size. Because in my opinion, that just makes sense, because they are they're fundamentally the same thing, but you might, in terms of memory, but they're fundamentally different in terms of their value. So you might make a different decision if you think that that doesn't make sense. And maybe as I use this language, I might say that that doesn't make sense, and I might come back in here and change that. And the good thing is, it's not like anybody's going to actually use this language, so I can make all the changes I like. But if you actually make something great and people use it, obviously just keep in mind every change you make might break like existing code bases. So it's very good for you to do a lot of testing before it becomes popular. But of course, that's, you know, being very hopeful. Unfortunately, most programming languages that people write are going to be seen by almost no one. But all that is to say is, don't really write a language with the hopes of becoming like, I don't know, becoming like a dominant language. It's more about learning how the process works. And there is the side benefit that maybe if you are familiar with a lot of languages, you could design one that is actually better. And if you know how to, I want to say market it, but not like in a financial sense, just in a like, hey, do you guys want to use this type thing? Then maybe you could actually transform the landscape. And I don't want to put you off from hypothetically transforming the landscape, because that would be nice and that's good. And there could be somebody watching this in the future that could do that. So don't give up on that. Just recognize that if that's to happen, it's going to be very challenging. So we've ruled out all the integers. Now, what if the thing we're trying to coerce to is a real? And notice, because of how we've done this, if we had this in the opposite order, it wouldn't work, because integers are reals. But now what we know is that this is only real in terms of like real is in the base name. So if what we're trying to coerce to is a real number, then, well, if we're an integer, we can just convert, or if we're also a real and we're smaller, we can convert. Otherwise, we can't. So it's, this right side is exactly the same as before, if you can see that pattern, but we also need the additional thing that if we are an integer, then we can do that cast. Lastly, we're assuming that this thing is a complex number. So just like previously, well, if we're a real number, which means we're an integer or a real number, then it's valid. Or we could say is number, but we already know that we're a number. So if we're smaller, then we return the type, otherwise null. And so this is a bit more, I don't know, like just a stronger sort of coercion system than what we had previously. And you'll also notice that overall, there's not like too much code, especially when you consider it's just the one file. Now, we want to make a companion object because Kotlin decides that that's the way we make things static. And we can make an operate on thing. This takes 2 expression types. The second one being nullable because we want to be able to apply this to unary types that only operate on unary operations that only operate on one thing. And it returns a nullable expression type. So, if T2 is null, this is the case where we have a single operation, we can return if T1 can be operated on, then we just return T1 because it's valid, otherwise null because we can't operate on it. That's pretty simple. Now, if we cannot operate, now if we have both of them, if we can't operate on T1 or we can't operate on T2, meaning we can't operate on at least one of them, we can return null because we have to be able to operate on both of them. Now, in order to allow that sort of natural and int intermingling that I was referencing before, where if you have like a nat64 plus an int 32, that should result in an int 64 because it should still be signed. And again, the more I like design this type coercion system, I kind of see why languages choose to not involve type coercion at all. Because something that somehow I overlooked is the fact that in Kotlin, you actually can add things like this, but that isn't because of type coercion, that's because of type generics. And this is, it's essentially an overload for the plus operator function, where one of the things just isn't an int. So maybe, I don't know, again, I might end up stripping a lot of this out, because I don't know if coercion is actually the best idea. But for now, we're going to go ahead and do this. And I guess this is still valid for me to put in a tutorial, because at least it showcases how you could do coercion if that's what you want in your language. And then if we want to take that out, we can in the future. So now if these things are both integers, then we have to do that fancy stuff that we were talking about, and I put that into a separate function called merge integers. We'll write that in a moment. And lastly, if at least one of them isn't, we have to just try coercing one to the other. Just like before, t2.coerce to t1. And now we can write our merge integers. T1 is an expression type. T2 is an expression type in this case. We already know that it isn't null. And so we also know that since they're both integers, we also know that this will always succeed. So we don't need to worry about an optional. Similarly to before, we want a size. But what we want is actually the largest size between them, right? Which is why we needed max defined. We can say t1.base.size, which we know exists because we already checked it's an integer, and t2.base.size, and whichever is the largest, we want that to be our new size. And now, we don't know if our end result should be natural or int, so I'm going to make a generic solution instead of doing like logic to figure this out, so that we just get like either base, and then we'll figure it out. We'll do the logic after we've gotten the size matched up. So if our size is 8, then we want one of these two things. It's either going to be a nat8 or an int8. And then it's exactly the same going down. If it's size 16, then it should be nat16 or an int16. 32u pair base.nat32 base.int32. 64. Could copy paste, but I'd kind of rather just do this. And lastly, you could say uint.maxValue here, but since Kotlin tends to cry when your when expression is being assigned to something, and it doesn't have an else, because what happens if this thing isn't valid? So it's better that we just throw in an else here anyways, and then that means we don't have to do the big uint.maxSize thing. which is less typing, which is good for us. And in that case, when we do have that uint thing, we just return the maximum ones. So now what we want to know is, should our end result be nat? And I'm going to just refer to that as isNat. And it should only be natural so long as both of the starting types are natural. Otherwise, if one of them is int or both of them is int, it should be int. So we can just return an expression type. There are like other properties we're kind of ignoring, like the dynamic and the optional, but that's not too big of a deal because if we're operating on it, well, actually, that's the big thing, right? The dynamic doesn't affect operations, at least the way we're going to do it. And we've already actually checked that T1 and T2 are not optional, because if either of them is optional, then they can't be operated on. So by the fact that we're here, we know that they will not be optional, so we actually don't even have to worry about it. And then what we want to do is give this expression type a base. Well, which base? If it's a nat, then it should be the first of those, because bases is going to return one of these pairs. So if what we want is the first of the pair, if we're nat, otherwise we want the second. And so that's our current up-to-date expression type class. Overall, I think it's an improvement over my previous one where we just had two almost identical files for like basically no reason. But I just needed some way to figure it out mentally. I had to design something, and I didn't want to just leave you guys without an episode for like 2-3 weeks. So hopefully you don't mind the refactoring. But it's also good because it shows the process. So we haven't actually really worked much on our verifier yet. Just a little bit. So let me go over there. Firstly, we don't need this basic type anymore because that doesn't exist. And one thing I haven't added at the top yet is this. We want to set our stage verb. And you can call this whatever you like. I'm calling it verifying. And what that means is, again, every time we have an error in our verification process, it will say verifying error, or verifying failure, or verifying warning. In order to print stuff, we're going to have to mess around with the node class, but I'm not going to do that until we actually get the long compile time values of numbers and stuff. Because we'll have to go back and modify it anyway. So we can do that after. And this is going to be hopefully not too crazy. Doesn't look too bad. So what we want is an operate on, which again is going to take... It's going to operate on two expression types, where the second one is nullable because maybe we have like a plus x, which only takes one thing. It only operates on one thing instead of two. It's not a binary operation. And so how can we care that this thing might be null? Well, the first thing I did was I said, okay, types is the list of T1 and T2, and then we can just say filter not null. But actually, in Kotlin, you can actually just say list of not null, and that essentially does the exact same thing. And that guarantees that there will be no nulls in that list. Then what we can do is we can loop through every type in the not null list, which is either going to just be T1 or it's going to be T1 and T2. And then if we cannot operate on this thing, then we're going to throw an error and say cannot operate on type $type. And if that error happens, we want to return something, and what we should return is just types.last. Because I tend to return the second type, but we don't necessarily know that T2 is not null here. So we're just going to return the last one, which means if T2 is null, it will return T1, otherwise it returns T2. It doesn't really matter because it's an error. We just need something to sort of continue to exist so that there aren't other types of errors that we have to handle down the line. In fact, if I go up here, you'll see, even though we had this cannot operate on string and int32, if I come down here, you'll see, okay, the string literals of type string, but it thinks that the additive expression is of type 32, int32. And that would just be because we're adding a string in an int32, and even though it fails, it returns the second one. And so if you can operate on both of those, then, well, let's actually do that. We can now call ExpressionType.operate on T1 and T2. But just because you can operate on them individually doesn't mean you can operate on them together, which is why we designed the whole ExpressionType.operate on function. So if type is null, that means we actually failed in that operation. And we can throw in error. And we can say that we cannot operate on T1 and T2 because we can't operate on them together. Otherwise, what we want to do is we want to return type, but type might be null. So if type is null, we just return types.last again. And then anytime we do an operation, we can just call this. Now, there are some other useful things we can do. For example, arithmetic operations and bitwise operations have different rules. For example, in our language, you can't do arithmetic operations on things that are not numbers, and you can't do bitwise operations on things that are floating types or non-integers. So we just have to handle those. We can create an arithmetic operate on, which is going to be basically the same thing otherwise. And we're going to actually just call operate on here, so that if you can't operate on them individually, then that's like a failure. But if you can, you end up with the other type. So the only thing you have to keep in mind is you're going to end up with, hypothetically, a handful of error messages for one error doing things this way, but overall I think it's fine. And then if type is not an integer, and we know that it isn't null because we don't allow operate on from the verifier to return null. But if we're trying to do, oh, I'm reading the wrong one. Right. If we're trying to do an arithmetic operation on something that is not a number, and again, notice this is the merged type, right? This is the deduced operate on type. So if we're trying to do that, we cannot perform arithmetic operation on a non-number type. And I also want to type out the type so that they could see specifically which one is the issue. And return type. Although, looking at things this way, I guess it's fine the way we're doing things, but yeah, the error messages are going to be a little strange, so I'll probably get to tweak this as well. But lastly, we can also do the bitwise operate on. T2 is also an expression type, but it's nullable. It's going to be basically the same thing, though. We can say operate on T1 and T2, and then if the type is not an integer, then we have an error. Cannot perform bitwise operation on non-integer type, and we can then return type. And that's pretty much all there is for the verifier. But I think now we actually have to go implement this. So I do call verify, but I'm not actually using any of the verifier parts. Everything is just becoming of type unit. So let's go up. We have a handful of things, but we should probably start with the primary expressions. So let's go start with our num literals. And what we can do is we can now, for the first time, override our verify function takes in a verifier, and returns nothing. So, first things first, when we have a number, there's three possible types we could have. If this thing is complex, then by default it should be a double complex number, because in C, the language we're transpiling to, doubles are the default if you're just like typing a literal. So we can say that the base is like this thing. If our imaginary component is not null, meaning we actually have an imaginary component, well, then this thing ought to be a C-plex 64. Otherwise, if the token is an integer, meaning it's not imaginary, it's real, but it's an integer, well, then it's just an integer, which I'm choosing the default integer type to be int32. Otherwise, it's just a real number, which by default is a real 64. And we could just set our expression type to a new expression type using this base. And that's it. And this is the foundation of essentially our type inference system, because like I've mentioned in the past, other languages will infer the types of things based on how you use them. But in our language, the type is going to be known at the moment that the moment like a variable is declared, the type needs to be known. And the way we do that, because you have that discussion of like, val x is equal to 5. Well, what should x be, right? Should it be an integer? Should it be a real number? In my opinion, we can just say 5 is an int32, and therefore x is an int32, and that's the type inference. And if you don't like that, well, you can either cast this, or you can just specify a different type, and it will work. So I don't think that's too big of a compromise, in my opinion. I haven't come across, like, because here's the thing. I don't think Kotlin works the way that I'm describing. I think Kotlin does the, like, based on how you use it, it will figure it out. But I've been treating Kotlin as if it does what I do, or what I plan to do, and I've run into no issues designing this whole thing. Which to me means that, like, extra sort of inferencing power, I don't think is really that often useful. It really just seems like a tool for laziness more than anything else. But maybe I'm wrong. I haven't done that much programming, especially in languages like Rust or Kotlin that do that. Anyway, char literal should be very similar, except it's actually much simpler. At least for now. You see, actually getting the value is going to be a pain because we have to figure out what the character is and what the ASCII value is. But when it comes to just the type, well, that's very easy. We just have to set it to type char. Expression type is equal to a new expression type base.char. And that's it. Same thing. In fact, I'm going to copy paste this for the string, because the strings is essentially the exact same thing. It's just instead of char, it's just going to be string. And let me just guarantee that that's all it is. Yeah. Identifiers, for now, all I'm going to do is I'm going to override this with the verifier, and I'm going to just set it to any. But something you have to realize, we don't actually have variables in our language yet. So this kind of is a moot point, like it just doesn't matter. We're not actually using this because we haven't created the syntax to allow people to assign variables, which means identifiers are essentially always invalid for now. So what I'm just going to do is give it a type any and just not care. Now, primary keywords are a bit interesting. I believe in our language here, if I just quickly go over to our token class, you don't have to follow me. Our primary keywords are simply true and false. We don't have a none. So let me go back to the verifier. And then, no, not the verifier, the primary expression. Yep. And let's override this. Override fun, verify. Verifier is a type verifier. I'm still going to set up all of the logic for when we do add null, because it's really minimal logic. It's 4 lines. In fact, it's 3 lines. But is none is never going to be true, at least not yet. But we can set it up here. So, well, is this thing none? Well, it's true if token has none, which will only be true if you type in the identifier, which will never be a primary keyword yet. And then our base is, well, if is none, then it's of type any. Otherwise, expression type dot base. Otherwise, it's a Boolean, right? It's true or false. This is complaining because we're not using the value. And lastly, we can set the expression type. I think I'll move it up here to be the expression type using the base. And if it's optional, it should be optional if it's none. And this is the only time currently that we actually have this, because again, we don't have variables. And parentheses expressions are pretty simple. We can override fun verify using a verifier. And all we do is we say expression type is equal to expression.expressionType. Because if you recall, if I go to node, oh god. Yeah, there we are. If I head into node and go to the second, you see in our verify node, before verify is ever called, we already compiled each of the parts or verified each of the parts. So by the time this verify is ran, the internal expression will have already been verified, so we can just take its type, because that's essentially it, right? The type of the parentheses expression is just the type of whatever's inside, so we don't have to actually worry about that. Okay, so that's the first step. Next, we can just work our way up in the grammar. So actually, I want to see this. I still haven't done cast expressions fully yet, but I'm not going to worry about that yet. Let's go to exponential expressions. And these are going to be very simple stuff. Probably going to be a copy-paste job, if I'm being honest. So to get what's the expression type of the exponential expression? Well, we can just say, we can use our verifier, oh my goodness, arithmetic operate on, where we pass in left expression type and right expression type. And that's it. So I recommend copying this, because we're going to go paste this into some of the other ones. Do keep in mind, though, you don't want to just like you don't want to like quickly just say, well, let's go put this in the into like some superclass or whatever, because again, you'll notice when we're actually storing the value, we're going to be expanding this verify. So it's only like for now. Go into multiplicative expressions. Literally, all we need for now is this. But in the future, we need to do other stuff. And then if we go over to additive expressions, it's also the same. We're just getting the type by calling arithmetic operate on. And then there are a handful of other expressions we've already done. Let me see. Actually, are there? I don't think there actually are. Primary expression, multiplicative expression. Those are the only ones I've actually implemented in the series with you guys, which is okay for now. Let me go into our nodes then, because I do need to change this, right? This would have been a problem. We have to change our basic verify to be, instead of basic type, expression type dot base dot unit. So let me see if this actually runs. Or if I need to change anything else. So obviously it's probably going to throw some error because, yeah. I'm kind of okay with this. Again, I did talk about previously allowing stuff like this for Boolean arithmetic. I might make a rule that that's allowed at some point, but for now, it's working as intended. it's really hard to make these very arbitrary decisions. Like, is anybody even going to use that if I decide to allow it? Is it going to be too annoying if you're always having to cast things? So I'm not too sure about that yet. But I think otherwise we're in a reasonable state. I mean, we could sort of do... We should probably do part of the printing because I do want to see everything. So we can modify our tree string. All we have is the expression type. We don't have the value yet, but that's okay. I'm going to forget the shortcut, but I'm just going to move this up here. And then we can just do a simple check. So there's a new thing with late init vars in Kotlin. It's relatively new, I think. We can check if it's initialized at runtime. So we can do the : thing to reference like the actual sort of like property rather than its value. And we can say, is it initialized? And if it is, then what we can actually do is we can add the expression type to it. And I'm only going to do that here. You could go down to primary node and add it as well. And every other place that you override the tree string, you might want to do that. You could also sort of... I think what I'm going to do, actually... Let me just quickly design this. Or should I... I'll just do it right here, for better or for worse. Is that what I'm going to do? Yes. So I'm just going to make a private... And I'm going to call this... Well, it's a val, but it's going to be a field. And it is going to be called... It's essentially going to do this whole two-line thing for us. And this is live coding, so it's going to be a bit slow, especially since my head is super tired, but I just want to give it a good name. Something like... something, a good name, like name and... Yeah, like name and type. Just something simple. And it's a field, and it's just going to return... do I have to... I don't know if it can interpret that as a string. If I did this, yeah, it probably can. So really what I want to say is, it should just return. There's a few ways I can... Let me try something like this and see if I like how it looks. Class.simpleName followed by $if expression type is initialize. Then it's $. No, I hate that. That's awful. I'll basically do the exact same thing I had before. So I'll just come down here. I didn't mean to do it one at a time. This is not going great. Okay, let me just yeet that out of there. Paste it. And then just return string. Oh, because the equals. Yes, and then what I can say here is var string is equal to name and type. And then what we can do is in the primary node, instead of doing this, we can just say name and type. Cannot access, it is in, because it's a private thing. So actually what I want this to be is protected in principle. Yes, and I think there was one other node, maybe one of the primary nodes, where I overrided the tree string. I did num literal. So I'll come in here and I will say name and type. Was there anywhere else that I did tree string? No. And let me just quickly, I think I made a... I don't think it was a mistake. Yeah, but I don't need these anymore. So that's good. So now let's try printing this. And of course we haven't printed our verifier yet, but that's fine. But it compiles. So what we want to do is we want to go into our verifier again. And we want to just add above verify tree, just a simple override. Override fun to string, which is simply equal to $tree. It's just going to print the tree again. But at this point, those late init properties will have been initialized. And now, if we go to app.kt, in the run verifier thing, instead of printing verified, we can actually say verified AST, new line, 4 spaces, and we can just print the verifier. Now, if we do this, you can actually see these types are printed out. And we can see that the type actually was like deduced properly. This is of type char, this is of type char. And you see our parentheses expression is working. You see that our statements are all of type unit by default. But everything has a type and they're all being printed. This num literal is of type complex 64 because it is a complex number. This is int32. When we multiply them, we get a complex 64. And that's all placed into a string. Like it's working. It's working very well. So I think that's a big improvement from what we previously had. Hopefully my tired brain hasn't been too hard to deal with in this episode. But in the next episode, I think we'll start work. We're either going to work on adding more nodes for our grammar, or we're going to start work on the expression values so that we can actually sort of calculate compile time values. While that's not that hard to say. It's probably about time that I end this episode, so I hope you guys enjoyed, and I'll see you in the next one.